Today on AI Paper Slop, we are jumping straight into a paper from June 26, 2026, called DanceOPD, On-Policy Generative Field Distillation. This is from researchers over at DanceOPD, NUS, UMD, and HKS.
Yeah, and just to give you the immediate core insight here, modern flow matching image generators, they fundamentally struggle to combine different capabilities.
Right, like trying to do text-image, local editing, and global editing all at once without completely degrading the model's performance.
Exactly. And DanceOPD basically solves this multi-capability bottleneck. They use this really novel on-policy generative field distillation framework.
Which sounds like a mouthful.
Yeah.
But they treat each capability as a velocity field, and they introduce three very specific architectural fixes to make it work.
Right, so you've got hard-routed sample-wise matching to stop target field ambiguity. You've got on-policy field querying on the student rollouts, which fixes the state distribution mismatch.
And then the third one, which is super interesting, a semantic side single query to avoid trajectory correlation. And, they tie all of this together with just a really simple velocity mean squared error objective.
Yeah, and the end result is a model that drastically improves how these capabilities compose while being computationally way cheaper than existing dense on-policy distillation methods.
Right, so that's the high-level view. But I want to spend some time unpacking why this is such a notoriously difficult problem to solve in the first place. Because, the industry is just chasing this idea of a unified God model, right? A single model that handles every type of generation flawlessly.
Oh, absolutely. Everyone wants the one model to rule them all. But the underlying issue is that mathematically, these different generative capabilities are essentially at war with each other under the hood.
Yeah, if you think about it in physical terms, it's kind of like trying to train a single athlete to be an elite marathon runner, a competitive power lifter, and an Olympic gymnast, all at the exact same time, using just one generic workout routine.
That's a perfect analogy, actually, because the physical adaptations you need for one discipline actively degrade the physiology you need for the others. Like, if your athlete builds up the massive muscle density they need for powerlifting,
their marathon times are going to completely tank.
Exactly, because they're carrying too much heavy, oxygen-hungry tissue. And in the realm of image generation, our disciplines are text-to-image, local editing, and global editing. So with text-to-image, or T2I, the model is heavily rewarded for open-ended visual hallucination.
Right. It needs the freedom to invent complex structures purely out of thin air, just from a text prompt.
But then local editing demands the exact opposite behavior. It requires strict, mathematical pixel preservation of the original source image paired with highly precise targeted changes. It doesn't want the model to hallucinate freely at all.
It wants it to be incredibly restrained.
Yeah.
And then, global editing intentionally alters broad image-wide statistics, right?
Yeah.
Like shifting the entire color palette or modifying the whole global layout.
Right, which means the gradients, the mathematical signals that update the model's weights during training, they're pulling the network in completely opposite directions.
So it's basically tearing itself apart.
Totally. And historically, when engineers try to force a model to do all three, the naive solution is just throwing all the training data into a blender. They try data mixing or joint training.
But doing that dilutes the capability-specific supervision, right?
Yeah, exactly. You expose the model to these massive gradient conflicts. You have one gradient explicitly telling the model to hallucinate a novel background, and it clashes directly with a gradient telling it to strictly preserve the original background pixels.
And when you have two massive mathematical forces colliding like that, they usually just cancel each other out, which is how you end up with, a blurry, melted mess. Like if you try to change one neon sign in a cyberpunk city and the whole image just structurally collapses.
Right. That's the daily nightmare for people working in this space. And the alternative naive approach is parameter space merging. So, model soups or Lurai merging, where teams train separate specialized models for each task and then attempt to mathematically average their weights together after the fact.
But averaging weights just gives you a compromise solution.
Exactly. You're not getting an elite runner and an elite lifter. You're getting someone who's just kind of mediocre at both.
So if mixing the data creates a blurry mess and averaging the weights gives you a watered-down model, how did the team behind DanceOPD actually approach this? Because clearly the standard toolkits are failing.
Well, they realized they needed a totally different mathematical perspective. So instead of fighting within the confines of data or weights, they turned to flow matching formulations. They chose to reframe these distinct capabilities as velocity fields.
Okay, flow matching is a term that gets thrown around a lot lately. Let's visualize this for you listening. I like to think of a flow matching framework as this massive, multidimensional weather map showing wind currents.
Oh, I like that.
Yeah, so on one side of the map, you have pure static noise. And on the far side, you have the data points, the clean, finished images. The model's entire job is to learn the wind currents, right? The velocity fields that will push a noisy static image across the map until it forms a clean picture.
That maps perfectly to the continuous state space of the model. So in this context, DanceOPD takes frozen capability sources, say an already pre-trained T2I model, a highly fine-tuned local edit model, and maybe a separate global edit model, and it treats each one as a distinct specialized wind current blowing across that exact same shared map.
I'm going to pause you there, because treating them as wind currents on the same map implies they can interact seamlessly. And the paper mentions this is possible because they share the same architecture, so we can compare their local Gaussian transition kernels.
Right.
That sounds incredibly dense. Can we translate that back into our weather map analogy?
Sure, let's break that down. A local Gaussian transition kernel is essentially just a mathematical way of describing the localized probability bubble at any given coordinate. So think of it as placing a highly sensitive anemometer, like a wind gauge, at one specific grid point on your weather map. Because all of these teacher models share the same underlying backbone family, the same latent representation, and the same way of parameterizing velocity, they are all operating on the exact same coordinate system.
Ah, I see. So you can drop your wind gauge at coordinate X and mathematically ask, at this exact microsecond, which direction is the T2I wind blowing and which direction is the edit wind blowing?
Precisely. You have a shared map, and you can read the specialized winds. And the paper states that training the student model, the single model we actually want to do everything, essentially boils down to a 3-part field query problem.
The 3 pillars.
Exactly. We have to answer 3 questions. First, which field should supervise a specific sample? Second, where in the state space should that field be queried? And third, how many states from the student rollout should be used?
Okay, so the way DanceOPD answers those 3 specific questions forms the causal chain of their entire framework. Let's start with the first challenge, deciding which field to listen to, which solves this issue they call target field ambiguity.
Right. So consider what happens if you try to average the winds. If you have a training sample and you average the velocity of the T2I teacher and the edit teacher together, you get a target vector that points somewhere diagonally in the middle.
Right, just splitting the difference.
But in the highly complex geometry of image generation, that middle direction might just point into an empty void. It doesn't correspond to any valid, meaningful image capability.
Going back to our athlete, it would be like instructing them to run a marathon while simultaneously performing a handstand. The instruction itself is structurally invalid.
Exactly. Which is why DanceOPD utilizes hard routing. Instead of blending the signals, the system dispatches each training sample to exactly one capability field.
Oh, so it's a strict one-to-one mapping.
Yes. If the system is processing an editing task, it strictly queries the edit field for the target velocity. If it's a text-to-image task, it strictly queries the T2I field. This perfectly preserves the semantic identity of the supervision. So the student model learns to compose these capabilities statistically over millions of distinct, hard-routed updates, rather than trying to average conflicting signals inside a single training step.
Okay, that makes sense. We've solved the ambiguous instruction by explicitly routing our student to listen to just one specialized coach at a time.
Yeah.
But that introduces a new problem, right? During training, if we just look at the teacher's perfect specialized path across the map, what happens when our student model, who is, trying to learn multiple disciplines, inevitably trips and wanders off that path during actual inference?
Yeah, you are hitting on the exact problem of state distribution mismatch. Traditionally, off-policy distillation evaluates the teacher's field on a fixed set of states, the perfect trajectory that the teacher itself generated. But your student model is inevitably going to drift. It will explore slightly different coordinates on the map.
Right, and if the student finds itself in an unfamiliar coordinate, and it has only ever been trained on the teacher's pristine path, it has absolutely no idea how to correct its course. It hasn't learned recovery.
To bridge that massive gap between training and inference, DanceOPD implements on-policy field querying. So instead of asking the teacher what it would do on its own perfect path, the system queries the routed teacher field on a stop gradient state drawn from the current student's actual rollout.
Let me make sure I've got this. It essentially drops the teacher into the exact coordinate the student has wandered into and asks, if you were standing right here In this messy situation, which way would you push the image?
That is exactly what it does. It aligns the supervision entirely with the states the student will realistically visit.
So we know which specialized wind to listen to, and we are measuring that wind on the student's actual path. That brings us to the third question. How many readings do we take along that path? The paper introduces a semantic side single query, meaning k equals 1.
Right, k equals 1.
And they look at a 16-step rollout, but they only query one single state per sample. I've pushed back on this.
Go for it.
If you are already paying the massive computational cost to generate a full 16-step trajectory for the student, isn't throwing away 15 of those steps a catastrophic waste of data?
I mean, it seems highly counterintuitive, right? If you have 16 data points available, traditional machine learning intuition screams at you to utilize all 16 to maximize your gradient updates. However, the authors identified a toxic trap in that intuition, which they call trajectory query correlation.
Okay, so how does that correlation corrupt the data?
Well, if you query all 16 steps along the exact same rollout, those states are not statistically independent. They share the identical text prompt, the same initial static noise seed, the same student dynamics, and the same compounding path history.
Ah, I see.
So accumulating dense correlated queries across a single trajectory doesn't provide 16 times more independent information. It actually amplifies bias without reducing the variance of the gradient.
Oh, wow. So if there's a slight error or a gradient conflict early in the rollout, querying every single subsequent step just repeatedly hammers the model with the exact same mistake.
Precisely. You aren't learning 16 new things. You are learning the same biased thing 16 times, which destabilizes the training.
That perfectly clarifies why they avoid dense queries. But it still leaves the question of why they choose just one step, and specifically why they use this mathematical distribution called beta 52 to bias that single query toward the semantic side of the trajectory. What does that actually mean?
So a beta distribution shapes probability, and a beta phi shape is heavily skewed toward one end of a timeline. In this case, it intentionally biases the single query toward the low noise end of the generation path.
The end where the image is almost done.
Exactly. Consider the very beginning of an image generation rollout, when the canvas is almost entirely static television noise. At that high noise stage, the model is merely performing generic structural denoising. It's just trying to find basic blobs and outlines.
Right. There isn't much task-specific intelligence required to pull a blurry shape out of static.
But as you move down the timeline, closer to the final clean image, the low noise side, that is where capability-specific information becomes incredibly dense. That is the semantic side.
Oh, so that's where the fine local attributes, the complex textures, and the intricate targeted edits actually materialize.
Yes. By querying just one single state in that semantic-rich zone, DanceOPD extracts a high-signal update without suffering the toxic correlation of dense queries.
So we have isolated our perfect, uncorrelated, highly semantic single query on the student's own path. The next logical step is actually updating the student model's weights. How are they calculating the error?
The elegance of DanceOPD really shines here, honestly. The student weights are updated using a plane velocity mean squared error, or MSE Objective.
Wait, I'm reading the background literature here, and usually field matching involves incredibly dense math. Things like Kale divergence, score-style surrogates, or consistency matching. I need a quick translation. Why are all those complex methods usually preferred, and how does DanceOPD get away with just plain MSE?
Well, those complex methods exist because probability distributions are usually messy. Kale divergence, for example, is a way to measure how much one probability curve differs from another. Consistency matching tries to ensure that any point on a trajectory maps to the exact same endpoint. They're heavy mathematical tools designed to wrangle uncertainty.
Right, they're dealing with fuzziness.
But the paper mathematically proves that under a local Gaussian transition view, a complex Kale-style field matching objective actually reduces down perfectly to a weighted MSE form.
Oh, wow. So because the target they're aiming for is a deterministic velocity field, a specific, known wind direction, direct, simple regression is sufficient.
It's more than sufficient. The ablations show it's superior. Plain MSE beat the time-step weighted variance, it outperformed the score-style surrogates, and it proved more stable than consistency matching. Direct regression is simply the most robust way to learn a deterministic target.
I see how that simplicity is a massive advantage. And that same direct MSE objective is how they tackle something called guidance field absorption, specifically dealing with classifier-free guidance, or CFG.
Right.
Now, for anyone building these models, CFG is a standard inference technique used to push the generated image to adhere much more strictly to the user's text prompt. But how does absorbing it save time?
Well, CFG requires evaluating the neural network twice for every single step of generation, once conditioned on the text prompt and once unconditionally, and then you extrapolate between the two.
So a 16-step generation actually requires 32 forward passes.
Exactly, which is incredibly computationally expensive. DanceOPD bypasses this entirely by treating the CFG vector as just another velocity field and absorbing it directly into the student model's weights during training, using that exact same MSE objective.
So the model inherently knows how to follow the prompt heavily without having to do the math twice at runtime. That is a massive win for latency. But the authors highlight a critical practitioner trap here regarding CFG scales, don't they?
It's a very dangerous pitfall. When you absorb CFG during training, you bake in a specific scale, let's call that training scale alpha. If an end user or an engineer unknowingly takes your distilled model and applies an evaluation CFG scale, let's call it beta during inference, those two values compose multiplicatively.
Wait, so if the DanceOPD model baked in an alpha of 3.5, and I read it in my pipeline with a standard beta of 2.
You are effectively hitting the image with a CFG of 7.
Oh no.
Overguided composition will absolutely fry your image, causing severe color saturation and deep structural artifacting. The learned field gets damaged by the multiplier. You must be deeply aware of what guidance scale is already baked into the weights you are deploying.
That is such a good warning. And it brings up a great point about what is baked into the model initially. Does it matter where the student model starts its training? Like, does initialization impact how well this MSE objective takes hold?
It has a tremendous impact. Because this is an on-policy method, the initial student rollout determines exactly where the teacher fields are queried early in the training process. The authors found that initializing the student with a checkpoint that holds the strongest relevant capability specifically, the local edit initialization dramatically outperformed starting from a merged checkpoint or a base T2I checkpoint.
Really? How big was the difference?
Massive. For example, using the local edit initialization improved the subject removal metric by an astonishing 124% compared to a merged start. A stronger initial student rollout simply provides a better foundation for the hard-routed field matching to take effect.
The theory is super cohesive, but the real test is whether a model trained with a single hard-routed query can actually survive complex benchmarks against dense multi-teacher baselines. So how do the empirical results actually stack up?
The data is highly compelling. When composing text to image with editing tasks, DanceOPD improves the GDIT bench average by 8.1% over the absolute best on-policy distillation baseline. Furthermore, it even beats the dedicated local edit source model by 7.9% for composing local and global edits.
That is wild. It isn't just matching the teachers. In complex compositional settings, it's actually exceeding them because it resolves the underlying gradient conflict so cleanly.
Right. And regarding that realism field absorption we discussed, it successfully closes 85.3% of the student-to-teacher reward gap, all while preserving the baseline text-to-image performance without any degradation.
There is a fantastic qualitative example in the paper that makes this incredibly concrete. The water bottle. The model is given a standard source image of a plain water bottle, and it is tasked with applying 6 wildly diverse extreme edits.
Yeah, that example is a great showcase.
It adds realistic, ice-cold condensation drops. It changes the material composition to a rose gold metallic finish. It transforms the bottle into a technical exploded diagram. It even executes a transparent glass reveal.
When you review those visual outputs, what do you think is the most striking technical achievement?
For me, it's the flawless preservation of the original geometry. Throughout all 6 of those extreme global transformations, the model perfectly preserves the bottle's core identity. The specific cap shape, the upright composition, its central placement in the frame, it's all untouched. It binds the object perfectly while successfully routing the distinct capability required for the edit.
That is exactly the hard routing and semantic side querying working in tandem. And perhaps the most vital takeaway for engineers looking to implement this is the compute cost. Because DanceOPD uses k equals 1, just one single gradient state per sample, it completely undercuts the computational complexity of existing baselines.
Right, because a baseline like DiffusionOPD computes gradients for all 16 steps of the rollout, which incurs what the paper calls a massive k-dense penalty.
And another baseline, FlowOPD, relies on an algorithmic grouping strategy called FlowGRPO. That strategy requires splitting groups across multiple microbatches, which introduces severe memory and compute overhead. By relying on a single semantic query, DanceOPD completely sidesteps all of that bloat.
I do want to circle back to something you mentioned earlier about trajectory query correlation, because the methodology the authors used to prove their theory is brilliant. They didn't just assume dense queries fail because of correlation. They actually proved it using a diagnostic called SDE decorrelation.
It's a phenomenal piece of scientific rigor. To definitively prove that the correlation between sequential steps was the culprit, the authors intentionally injected stochastic noise, specifically an SDE, or stochastic differential equation rollout, into the student's path.
Let's use an analogy here because stochastic noise injection is pretty dense.
Yeah.
Think of a 16-step student rollout like a heavy freight train with 16 connected train cars rolling down a track.
Okay, I'm with you.
If you take speed and sway readings from all 16 cars, your data is highly correlated because they are physically coupled together. If the engine derails, car number 12 is going to derail too.
Right.
So injecting SDE noise is the equivalent of uncoupling those 16 train cars and putting them each on slightly different rough terrain to see how they perform completely independently.
That is exactly the mechanism. By injecting that random mathematical noise at every step, they broke the deterministic link between state 4 and state 5. They decorrelated the train cars. And when they ran the dense query baseline on this newly noisy, decorrelated path, the performance actually partially rescued itself. It saw an 18.4% gain.
Which scientifically isolates the variable. The dense queries were failing specifically because they were coupled too tightly.
But crucially, even with that decorrelation rescue, the single semantic query DanceOPD's k=1 approach still safely beat the decorrelated dense version by 8.6%. It proves that the single semantic side query isn't just cheaper, it is a fundamentally superior, safer default for training.
As we wrap up this analysis, there's a critical assumption built into DanceOPD's architecture that we really need to highlight. The entire system relies heavily on predefined routing.
Yes, that's a big one.
It assumes the training pipeline explicitly knows ahead of time that an incoming image sample is definitely a local edit task, or definitively a T2I prompt, or strictly a global style change.
Which works perfectly for benchmarking scenarios where the training data sets are neatly bucketed and labeled.
Right. But what happens in production when task boundaries become ambiguous? Like, what if an end user inputs a massive complex prompt that requires several capabilities simultaneously? Something like change the background to a cyberpunk city, but also turn the apple on the desk into a crystal and make the whole image look like a 1990s anime. You can't just route that to one single coach.
That ambiguity is the absolute frontier for flow matching distillation right now. The next necessary evolution might be integrating dynamic reward models or verifiers that actually route these queries on the fly based on predicted edit success.
So the model would have to figure out its own routing.
Right. It would require bridging the gap between this field-routed distillation and reinforcement learning from human feedback, allowing the model to weigh capabilities dynamically, maybe even per pixel.
It's a fascinating trajectory for the field. We started by looking at the seemingly impossible task of training a single athlete to be a marathon runner, a powerlifter, and a gymnast simultaneously without ruining their physiology. And DanceOPD proves that you don't need to force a compromise routine. You just need to know exactly which specialized coach to listen to at the exact right high signal moment on the track. Definitely something to mull over as you design the architecture for your next generative training pipeline.